Okay, guys, this is the second to last talk this semester. We have one more on the 18th, but today we have Eileen Gonzales, who is a Pegasi 51B fellow at Cornell. I think you just started this fall, so she's fresh. Yep. And she's going to be talking about stellar atmospheres. So if you can go ahead and try to share your screen.
Okay. Okay, can you guys see my screen? Cool.
Looks good.
All right, so like Angela said, I'm Eileen Gonzales. I am a postdoc at Cornell University, and I'm going to talk about my thesis work on understanding atmospheres across the stellar-substellar boundary. So first, an outline. I'm going to give you guys an introduction to brown dwarfs and subdwarfs, and then I've broken up my thesis work into two parts. The first on using an observational-based method for understanding fundamental parameters and atmospheric features, where I'm going to talk about my very first paper. And then the second half is moving towards a more theory-based approach with using atmospheric retrievals. I'm going to talk about my latest work on the binary SDSS J1416A and B. And then there's a comparison sample I have to 1416A to try to probe into some deeper questions. And then I'll briefly talk about things that I'm starting right now as a postdoc. Okay, so brown dwarfs are objects that straddle the mass boundary between stars and planets. They weren't first theorized to exist until the 1960s, but they weren't actually detected in the 1990s until infrared technology had improved. Unlike stars, these objects never get hot enough to sustain, say, hydrogen burning. So they start off as hot as they're going to be, and they cool over time. So they have temperatures that range from about 250 to 3000 Kelvin, all while having about the same size radius as that of Jupiter. They have spectral types broken down as to late M, LT, and Y dwarfs. And it's actually really hard to determine their ages because as they cool, they move through these spectral types. So you could start out as a late M dwarf and then cool down to a T, or you could be formed as a T. So we can roughly break them into three main age groups. So field age, which is about half a gig a year to 10 gig years. Low gravity or young objects, where we can define those by spectral features that stand out or being in nearby young moving groups. So those objects have ages of about 500 million years or less. And then old objects or subdwarfs, and those also stand out with their kinematics, and those have ages of about 5 to 10 gig years. So for my thesis work, I'm primarily focusing on these older objects called subdwarfs. These just have metallicities lower than that of the sun. And they can either be very old low mass stars or very old brown dwarfs, depending on their mass. Their kinematics exhibit consistent membership within the galactic halo. They have unusually blue near-infrared colors, and special features that stand out are enhanced abundances of metal hydrides, low abundances of metal oxides, and increased strengths of alkali lines. So these objects are really interesting to look at if you want to understand how metallicity affects the features we see in spectra. So for brown dwarfs, because these objects are very cool, their atmospheres are very complex, covered in molecular features and clouds. So when you look in this figure, as you move down, you're moving to deeper, hotter, and denser layers. And as you move right to left, you're moving from hotter objects to cooler objects. So interestingly, within the atmosphere of Jupiter, you can find all the different variations of brown dwarf atmospheres. So if you start with the atmosphere of Jupiter and you peel off the top cloud layers down to the methane gas, you move to a T dwarf, which can either be a cool brown dwarf or warm planet. Peel away even more layers down to the CO gas, you move to L dwarfs, which are warm brown dwarfs or hot planets, and you peel away even more, and then you're moving to the very cool low mass star regime. So for my work, I primarily focus on L dwarfs, but for the first half, I'm going to extend into these hotter M dwarfs, and then the second half of my work with retrievals, I extend to the cooler T dwarfs. So now that you have a little bit of a background on brown dwarfs, I'm going to jump into my first part of my work on understanding fundamental parameters and atmospheric features using SEDs. So the first work I'm going to talk about is using this particularly strange subdwarf SDSS J1256 to kind of try to probe and understand the population of subdwarfs themselves. So this object was chosen because it's actually very strange and it stands out from the rest. It was discovered in 2009 by Servani et al. In a survey for searching for L subdwarfs in SDSS DR2. Pre-Gaia, it was actually one of only 12 subdwarfs typed SDM7 and later that had a parallax. And currently with Gaia, it's one of the latest type objects that have a parallax because it's relatively nearby. It's one of the bluest L dwarfs. It's also one of the fastest tangential velocity objects. And it's spectral typed as an SDL 3.5. It's got a temperature of around 2300 Kelvin and a bolometric luminosity of minus 3.6. So to place it in context, we wanted to compare it to other objects of either a field age or younger. So in this figure, we're looking at the near infrared J-K color on the y-axis, and then the x-axis is spectral type. And you can use that as a temperature proxy for field sources. So you have the field in black and the 1 sigma in gray. So if you look at objects of the similar spectral type, you see that young objects appear to be redder than the field, while old objects appear to be bluer. So you can use J-K color as a proxy for age. So if we place 1256 on this plot, you see it really stands out compared to these other old blue objects. So we want to really understand what's going on with this because it's extremely weird. So typically we compare things of similar spectral types, but if you do that, you find out that comparisons with spectral types really aren't enough. So here we have objects of 3 different spectral types, but first off, they're 3 different ages, and that means they could be 3 different metallicities. So that's useful if you want to probe how metallicity affects your spectral features. We also see they have 3 different ranges in cloud coverage, where young objects are likely very cloudy, while old objects are likely cloudless. And probably the most important thing is that these objects are 3 different temperatures, and it's temperature that's driving the atmospheric chemistry. So instead of comparing things of similar spectral type, I want to compare things of similar fundamental parameters. So here what I've done is I have created distance-calibrated spectral energy distributions, or SEDs. And here I have the SED of 1256. And what I can do is, having that distance, I can get out an empirical bolometric luminosity. And if I use that with an estimated age and a radius from evolutionary models, I get a semi-empirical effective temperature. So here we have 3 objects of similar temperature, but you can see there are 3 different spectral types. And if they're similar temperature, because atmospheric chemistry is driving what's going on, we would expect them to have 3 similar shapes for their SEDs. So when I plot up these 3 objects, we find out that their shapes look very different from one another. So compared to the field objects in gray, 1256 in blue and the young object in red are both brighter than the field and the optical. But as we move to the near infrared, 1256 becomes fainter than the field, while the young object remains brighter. So this is likely due to a lack of clouds in the atmosphere of the subdwarf. And while the young object is cloudy, what we're seeing is a redistribution of flux out to the longer wavelengths. So we're really seeing clouds are sculpting the overall SED shape. And if we want to probe into how secondary features such as metallicity or gravity could be impacting the spectrum, we want to look at the near infrared band by band regions. So I'm going to show you a couple of bands. So in the Y band, we have things that probe some cloud sensitive features, particularly iron hydride. So if we look at the wing forward band at 0.99 microns, we notice that there is a trend with age where the depth gets deeper as you move to older objects. So that's showing that we can probe deeper into the atmosphere because we don't have clouds blocking it out. Also, we see atomic titanium-1 in the subdwarf atmosphere, and that's also indicative of the inhibited condensate formation. Because this isn't condensing out into other clouds, we have atomic titanium sticking around. When we look in the J band, we have some gravity sensitive features, particularly sodium and potassium. For 1256, we don't have the sodium doublets because there was too much noise, but the potassium alone is interesting. So what you typically expect for a young object, you have shallower lines, and an old object, you have deep lines. So we see this trend for the 1.17 doublets, but when we look at the 1.25, we see that 1256 in blue shows these very shallow lines that you would expect to see for a young low gravity object. So because this was really strange, we wanted to place 1256 in context with other subdwarfs that had medium resolution data, so we can compare this to see if this is just a feature of 1256 or a feature of all of these subdwarfs. So here we have subdwarfs that have this medium resolution data with the cooler objects at the bottom and hotter at the top. And we see that all of these subdwarfs share this same feature. At the 1.17 doublet gives us that deep high gravity that we expect for these old objects, but for all of them, we're seeing this shallow low gravity feature for the 1.25 doublet. We looked to see if there was any trends with temperature, and we didn't find that. So really what this is telling us is the 1.25 doublet is a poor indicator of gravity for subdwarfs. And we really need to dig into why we're seeing this. One thought is we could be probing two different pressure layers in the atmosphere. So that could be driving this, but really we need more medium resolution data of subdwarfs to draw a stronger conclusion because we only have these 5 objects right here. So next I wanted to place subdwarfs in context with the larger brown dwarf population. And one thing I wanted to look at is mass versus spectral type. So again, we have field age objects in gray, young objects in red, and old objects in blue. So these were all determined again with the same SED method. But now we have in black our field age objects that have dynamical masses. And what we see is these dynamical masses agree very well with the field age objects from the SED method, showing that the masses that are derived for these models are doing a good fit. If we look at subdwarfs, however, we see that these are landing on top of some of these dynamical masses, and they're not landing very far above the field objects. So to figure out what's going on, we really need dynamical masses of subdwarfs. And in this sample, we have a dynamical mass for one object, which is J1416. It's a binary. It's got a dynamical mass in Cornell 2016. And comparing our value to theirs, we find that our mass for the system is underestimated compared to what they get from the dynamical masses, which is pointing towards the fact that these low metallicity models may in fact be underestimating the masses for these objects. So from this first part on 1256, the conclusions are for the overall SED shape, we're seeing that cloud effects are really driving major changes in the atmospheres. In these band by band regions, we see these gravity and metallicity features that are shaping these variations. This 1.25 doublet is a poor indicator of surface gravity, and we're still trying to determine what could be causing this feature. And lastly, these low metallicity evolutionary models may be underestimating masses for subdwarfs. So since I've gleaned as much as I can from this observational based work, I took a turn to using a more theoretical based method of atmospheric retrievals to dig deeper into subdwarf atmospheres. So first, a little history of atmospheric retrievals. They are an inverse spectral modeling technique that tries to make minimal assumptions about the physics involved. They were developed from remote sensing for Earth and solar system objects, and they've been used primarily in exoplanet science for a lot of work's been done with transiting planets and a little bit of directly imaged planets, but for brown dwarfs, it's relatively new. And this is because brown dwarf science has primarily been using self-consistent grid models where you include as much physics as possible and iterate through to get a model to come up with fundamental parameters of these objects. So for brown dwarfs, there's really only 4 retrieval codes right now that have been used. The first one is Chimera, that's focusing on the cool T and Y dwarfs, and that was written by Mike Line. The second is Brewster, which has been primarily used for L and T dwarfs, and that's been written by Ben Birmingham. There is the Helios R2 code, which has been tested on a couple of T dwarfs, and the newest code is a modified version of Hydra that's been tested on a single T dwarf. So for this work, I am using the Brewster code. So how retrievals work, as I said, it was an inverse spectral modeling technique. So you start with your spectrum, and based on what you see in your spectrum, you can come up with an assumed list of gases. You explore your parameter space. So using Brewster, I've been using the Markov chain Monte Carlo, or MCMC. And what comes out of your retrieval is a thermal profile that characterizes the atmosphere in pressure versus temperature space. And then you have abundances for the gases you put in. Additionally, you come out with a model spectrum. And what we find is because of this freedom where you're putting in as minimal physics as possible, the retrieved spectra tend to do a better job at fitting the data compared to the self-consistent grid models. So here our data is in black, and the value, this retrieved spectrum that comes out from the retrieval is in yellow. And you can see that's doing a much better job at fitting the data compared to the self-consistent Simone and Marley grid models in magenta and aqua. So I used Brewster for this because Brewster right now is the only retrieval code that's been built with cloudy brown dwarf atmospheres in mind. And to come up with the abundances in this, there are two different methods you can use in Brewster. The first is this uniform with altitude method, or I'm going to call VMR for short. In this method, you assume the gas abundance is the same no matter where you are within the altitude of the atmosphere. So that may not be entirely correct, but it gives you freedom to retrieve individual gas abundances. So in this diagram, you see there's many, many more parameters that go into your model if you use this method. Instead of doing that, an alternative is a thermochemical equilibrium method. So instead of retrieving individual gas abundances, you end up retrieving just metallicity and the C/O ratio, and those gas abundances are then pulled from a thermochemical grid. And the downside of this is the assumption that the values from the chemical grid are going to work for all of your objects. So there's kind of a trade-off for both of these. So with retrievals, the two big questions I wanted to ask is, one, are subdwarfs actually cloudless? And this is what we're seeing from work in the literature and my SED work. And secondly, how does the pressure temperature profiles of subdwarfs compare to objects of either a similar effective temperature or a similar spectral type? So to do that, I created two different samples. The first is a sample of L subdwarfs. So these are all of the L dwarfs that were in the 1256 work. Plus their comparative objects. And then the second is a sample of T dwarfs. And the first thing I want to talk about is this T dwarf, L dwarf binary, because we really want to understand how the pair have interacted together. And then I'm going to talk about placing the larger subdwarf sample in context by looking at 1416 alone. Okay, so first the results from looking at the retrieval of the binary SDSS J1416A and B. And like I said, these are both subdwarfs, so both of these objects are actually very strange. 1416A is the primary. It's an L dwarf. It's spectral typed dwarf subdwarf L7, so its spectral features aren't as extreme as these other subdwarfs, but it does stand out from the field objects. So it has an unusually blue near-infrared color, but not all of the features are very extreme. From our retrieval work, we get a temperature of around 1900 Kelvin, while from determining the temperature from SEDs, we get a cooler temperature of around 1700 Kelvin. The secondary, 1416B, is also very strange. It's a late T dwarf typed T7.5P, and the P is noting that it's very strange compared to other T dwarfs. For subdwarfs, there hasn't been a lot of work in classifying T subdwarfs yet. So a lot of objects in the literature that are classified as peculiar are starting to turn up to be T subdwarfs. It also has an unusually blue near-infrared color, but when you look at a near-infrared minus mid-infrared color, it flips to being unusually red. It's got a temperature of around 660 Kelvin, and these objects are widely separated from one another at about 84 AU, which makes it really interesting to understand, because they're so old, did these objects actually form together, or was one captured from the system still remaining around for this time? So the three questions we want to address is, one, did these objects actually form and evolve together? What are their cloud properties if either of these have clouds? And then what is their metallicity? So using Brewster, what do the retrievals tell us? So for 1416A, we see it's best fit by a power law deck cloud model. So you can think of a deck cloud like a thick fog where you can see down through to a certain point, and after that it becomes thick and you can't see. So in the middle of the figure on the left-hand side, in purple is the region where the cloud becomes optically thick. And that shading of blue up to the dashed line is where it drops from an optical depth of tau equals 1 to tau equals 1/2. And the gray shading on either side is the plus or minus 1 sigma confidence for the cloud. What we see is the cloud top location, so that boundary between the blue and purple is tightly constrained. However, the vertical distribution or the height of the cloud is poorly constrained. Your question might be, what kind of cloud do we have? And to figure that out, we would look at the intersection of that cloud top, so that boundary between the blue and the purple, compared to the pressure temperature profile, which is in black, with the 1 sigma confidence intervals in pink. And you want to compare it to these colored dashed lines, which are condensation curves. So on the right-hand side, it would be in gas phase, and on the left-hand side, it would be condensed. So ideally, we'd see one of these dashed lines intersecting right at the point of the profile, but we don't see that. The two closest curves we have is iron and corundum, and the thought for the cloud opacity we're seeing is that this could be coming from something called virga. So in the Earth's atmosphere, virga would be when droplets are raining down in the atmosphere, but they evaporate before they hit the ground. So what we could be seeing is either iron or corundum droplets coming down and causing this opacity. Next, if we compare our pressure temperature profile to self-consistent grid models, here we have solar metallicity sonora models as solid lines and low metallicity as dotted. In our region where it's most tightly constrained, we see that there is overlap between our models and the self-consistent grid models, showing them in good agreeance. On the right-hand side, the figure we have is the contribution function. The gray shading shows how much flux is coming from that pressure level of the atmosphere. So the darker it is, the more flux is that we're contributing to what we see. In magenta is the median gas opacity when it becomes optically thick, and the cloud is in magenta and the gas is in aqua. So if you look down, you'll see coming from lower pressure levels to deeper ones, you see which is contributing most to the flux. So majority of the time, the gas opacity is dominating, but in a very, very tiny region, we're seeing the cloud affecting our spectrum. So to place this in context with other L-dwarfs that have been retrieved using Brewster, we looked at the contribution function for the ones in Birmingham et al. 2017. So he has a very red object, J1224, and then a field object, J0500. And what we've noticed is the location of this median cloud opacity above the median gas opacity could be tied to the observed J-K near infrared color, with the cloud opacity being higher above for redder objects, and then you see it moving deeper and deeper into the atmosphere as you move to bluer objects. So to look at the comparison of our retrieved spectrum and the sonora grid models to the data, here we're showing the data in black, and we have the solar metallicity sonora models are solid lines and the low metallicity are dotted lines. You see that the grid models are really doing a poor job at fitting the spectrum overall, particularly here in the J band where none of the models are doing a great job. If we look at what we get from our retrieval, we see that we're doing a much better job, but there's still a few regions that we're having difficulties. One I want to point out are these iron hydride features. So in the H band, we see that we're doing a really good job at fitting it, and we're having difficulties fitting it in the J band. On the figure to the right, we're looking at our retrieved abundances compared to what we expect to get out from a solar metallicity model grid. Our abundances are the solid lines with the shading, and what you expect from the model grid is the dashed lines. So looking at iron hydride in blue, what we notice is that the maximum amount that we should see in the photosphere is much greater than what we end up retrieving. So this is pointing towards iron being condensed out into a cloud. And what we're noticing is we're trying to fit this higher up feature in the H band while simultaneously trying to fit the feature in the J band, which is deeper down in the atmosphere. And that's showing one of the problems with using this uniform with altitude assumption. While it's giving us the freedom to retrieve these different abundances, this is something that's going to come up where you have gas features like this where you expect them to be different abundances and different pressure levels. Another interesting thing that we notice is if we look at the alkali lines that are tied together, the sodium and potassium, as well as the water and CO abundance, we see that what we retrieve, again, is less than what is expected from these solar metallicity models. So this is pointing towards this object, again, having a low metallicity atmosphere. So while this is the winning model, we find that there is another cloud model that ends up being indistinguishable from this one. And that is a power law slab cloud model. And the way we're intercomparing models is using the Bayesian information criterion, or BIC. And from this table, you see a BIC between 0 and 2 means that there's no preference between the models. This has a BIC of 1.4. So this is telling us that the slab cloud model should be able to tell the same exact story as the deck cloud. And the big difference between the slab cloud and the deck cloud is that the slab cloud has a defined top and bottom in pressure space, while the deck cloud doesn't have a defined bottom. So what we're seeing for the slab cloud is that it's not constrained in location and pressure space as well as height. We're seeing that our retrieve profile still agrees with what we get from these model grids. And when you look at the contribution function, we're seeing the same story with just a very tiny region of the cloud opacity dominating over the gas opacity. So it's again telling us the same story. For 1416B, we see it's best fit by a cloud-free model, which is what we would expect for a late T-dwarf. Comparing our pressure temperature profile to the Sonora grid models, we see that there's good agreeance. And when we compare it to the retrieve profile from Lanadal 2017, which is in aqua, we see that our profile agrees, except for this shape in the upper atmosphere. And that is the least constrained region in Lanadal's model. So we're seeing that they still agree. When we look at 1416B's spectrum compared to our retrieval and grid models, we see again that our retrieval is doing a better job. The low metallicity grid model is doing a good job at fitting the data in the H and K band, but it's struggling to fit it in the Y and J. And we see the solar metallicity 600 Kelvin model does a good job in the J band, but struggles to fit elsewhere. When we look at our retrieved abundances, we notice for both methane and ammonia that we're seeing less than are expected from these the solar metallicity models. And while these are very tiny differences, we notice that these really drive major changes in the observed shape that we see, particularly at these cooler objects. And this is really driving changes that we see in the spectra and this minor chemistry. Placing 1416A and B in context with evolutionary models and what we get out from their SEDs, we're looking at radius versus bolometric luminosity on the plot on the left-hand side. The retrieval values are in black, and what we get from the SEDs are in pink. The bold lines indicate that that's a range of values coming from the SED, while the thin lines indicate that's the uncertainty. So for 1416B, we see that the retrieved value and the SED value agree. And what stands out is for 1416A, only the slab value agrees with the SED. The deck value does not at all. It gives us this very small unphysical radius. And this is coming from how we're trying to fit our radius in our retrieval. And it's coming from trying to scale the scale factor, which is R squared over D squared. This has been seen before. So in Sorahana et al. 2013, they used a similar method, and they came out finding that they were finding these very small radii. And this is actually something that is a big problem with a lot of retrieval methods. And it's still unknown on why we're tending to derive a lot of these smaller than expected radii. On the right-hand side, we're comparing surface gravity versus effective temperature. And now I'm also including values from the literature in green. For 1416B, we see there's agreements between all three. And again, for 1416A, we see only the slab cloud model agrees with the temperature, and the deck cloud doesn't agree. But for both those cloud models, the log G values are coming out in agreements. So comparing properties across 1416A and B, we wanted to look at their carbon to oxygen ratio and metallicity to try to understand their formation and evolution. For 1416A, we see no matter which cloud model we use, the C to O ratio agrees with 1416B, and we see the same thing for the metallicity. We do see a bigger difference in metallicity for 1416A. but we do have these very large uncertainties. So this agreement and a consistent C to O and metallicity is pointing towards these objects having formed and evolved together. So next, to answer those two bigger questions about subdwarfs being cloudless and comparing their pressure temperature profiles, I wanted to create a comparison sample to 1416A. So again, those questions were looking at objects of either similar temperature or spectral type. What are the similarities or differences between their retrieved pressure temperature profiles and other parameters? So to do that, I created the comparison sample from generating their SEDs. So here we have 1416 in dark blue, and we have its comparative object of similar spectral type in blue, J1426. From its SED, we see it's got a temperature of around 1500 Kelvin. And like 1416A, we see it's got a hotter retrieved temperature, and this time it's around 1700 Kelvin. And because we had this difference between the SED temperature and the retrieved temperature of 1416, we look at two different comparative temperature objects. So the first one, J0539, is an object that has a more similar temperature to the SED temperature of 1416A. Again, we see its SED temperature is cooler than its retrieved temperature. And the second object we have is J1539. Interestingly, this one has both its SED and retrieved temperature are identical at around 1840. And this one's really interesting because it's a variable object, and we think its variability is due to cloud features. So I want you to keep this in mind as we get to the results from the retrieval for this object. So looking at the spectral type comparison, J1526, we see it's best fit by a gray deck cloud. So the cloud is behaving the same across all wavelengths. Again, a brief summary of the very complicated pressure temperature profile plots. In purple, we have the median cloud, and then where you don't actually see the shading up to that dashed line is where the optical depth drops to a tau of 1/2. What we see here is, unlike 1416A, we have both the cloud top and the cloud height being super tightly constrained. If you question what kind of cloud we have, again, we look at that intersection of the condensation curves, the pressure temperature profile, and the cloud. So here we're seeing that intersecting with either iron or corundum, which could be our cloud. When we look at our pressure temperature profile compared to the models, we see that they don't agree at all. The retrieved profile is hotter in the upper atmosphere than you would expect from the models, as well as it being cooler than expected deeper down. When we look at the contribution function, again, we see a super tiny region where the cloud opacity is dominating over the gas opacity. And the bottom plot is comparing the pressure temperature profile of 1526 in pink to the two different profiles for 1416A. And what we notice is in the upper atmosphere where we're least tightly constrained, these objects agree, but when we move to the photosphere where we're more tightly constrained, we see 1526 is in fact cooler while 1416A is hotter. So it has a runner-up model, which is a power law deck cloud. We wanted to look at this one because it has a BIC of 2.4. So while it's not in the indistinguishable range, it is very close. And if you look at the figure on the bottom, we're plotting the pressure temperature profile for the winning model, which was the gray cloud, compared to this one. And we see that those are almost indistinguishable from one another. And something we notice is when we plot up the cloud features, we're finding a degeneracy between one of the values, the alpha value in particular. So this tells you how non-gray the cloud is, and it's a function of optical depth and wavelength. So if alpha is 0, then you have a gray cloud. A negative value causes it to be a reddening cloud, while a positive value would mean a bluening cloud. And that's something you wouldn't expect. So here we see we have this positive value, but for either side, we have these very large tails, which is consistent with it being a gray cloud. And what we notice is if you have this positive alpha value, and you also see that your cloud has almost no height to it, we're found that there's a degeneracy between the two, allowing a power law deck cloud to mimic the effect of a gray cloud. So moving to the temperature comparison objects, the first one we have is J0539. This is also fit by a power law deck cloud. So like 1416, we see that its cloud top is constrained quite well. And like 1526, we see it has this positive value of alpha and this region where the cloud height is almost not there. So we're seeing that it probably has the same features of acting similar to a gray cloud. When we look at its retrieved spectrum and comparing that to the sonoric grid models, so here we actually have the cloud free in solid lines, and we have the Simone and Marley cloudy models as dotted lines. We see that the grid models for cloudy is doing quite a good job. Again, our retrieval is fitting a bit better. And comparing the pressure temperature profiles in the region of the photosphere where we're more tightly constrained, we see that there's actually some overlap between 0539 and 1416, meaning that there's something that's more similar between these two objects as compared to 1526. When we look at the second comparative object, J1539, we're finding it to be cloud-free, which is actually really shocking because this is the variable object where its variability is thought to be due to clouds. So there's some interesting things that come out of the pressure temperature profile that points towards this cloud-free model not actually being the best thing. Some big differences we notice in the pressure temperature profile is in the upper atmosphere, we're seeing that our profile is cooler than we expect to the grid models. Typically, we've been seeing these to be hotter than we expect. When you look deep down in the atmosphere, the pressure temperature profile is turning to be almost isothermal. And we see this when we typically want a cloud to be included within the model. Another thing we notice is that the photosphere for 1539 is a lot wider than what we saw for 1416. And when we compare the three of them, we see that there's, again, some overlap in the most tightest constrained region. When we look at the spectrum of 1539 compared to the grid models, we see, again, the cloud-free are solid and the dashed lines are cloudy. We see that the cloudy grid model is actually fitting the data much better than cloud-free. So this is another piece of evidence pointing towards that this may actually be a cloudy object. When we look at the retrieved spectrum, we see that it's sharing sort of the same features as 1416A with the iron hydride, where we're doing a better job at fitting it in the H band, but we're having difficulties in the J band. So we look at the retrieved abundances, we're seeing the same story where our retrieved abundance is less than we should have for iron hydride. So again, we're trying to fit that shallow H band feature while simultaneously fitting the deeper J band feature. So like 1416A, this is pointing towards iron probably being condensed out in the atmosphere of this object. Another piece of evidence pointing towards this probably really having clouds. So what this is telling us is that the near infrared data alone can't fully constrain the cloud properties of this object, particularly because it's strange. And what we really need is mid-infrared data, which probes higher up in the atmosphere to help constrain the cloud properties of this object. So in conclusion from this part, for 1416A and B, we see that for 1416A, it prefers a cloud model, but it's indistinguishable between it being either a deck cloud or a slab cloud. For 1416B, we see it prefers a cloud-free model. And the C to O and metallicity between the two point towards a consistent formation and evolution together. For the comparison sample to 1416A, we see that there's a degeneracy between this power law value and the cloud decay height, allowing a power law cloud to behave like a gray cloud if you have this positive alpha. And we're also finding that we really need mid-infrared data to best constrain cloud properties, particularly strange variable objects. And last, I want to talk a little bit about the work I'm doing as a postdoc. So I'm moving away from looking at these old brown dwarfs to looking at young brown dwarfs as analogs for directly imaged exoplanets. So in this figure on the right-hand side, or the left-hand side, we have young brown dwarfs in gray and cooler brown dwarfs that are older in blue, compared to exoplanets and planetary mass objects in magenta and black. And we see there's a really good overlap in this region, showing that these young brown dwarfs are going to be great analogs for retrievals of these directly imaged exoplanets. And because for this work I am moving towards cooler objects, I am going to do some enhancements to the Brewster code base. For this work, I've primarily been focusing on these gray clouds or power law clouds, but there is a capability to test individual cloud species. A thing I want to include is potentially retrieving the imaginary index for me scattering. As we move to these cooler objects, we could be testing out and hitting a regime of disequilibrium chemistry. So another thing to put into the code to have something in between a free retrieval with those uniform with altitudes compared to the thermochemical equilibrium where you're pulling it from a grid is including a quench level to point out where things could be quenching for this equilibrium chemistry. And particularly with JWST proposals just passing by, getting mid-infrared data from MIRI is going to be really important in retrievals to really dig into what's going on with the cloud features of these objects. And it's really going to allow us to start individually picking out which cloud species we have. And with that, I will leave it and take questions. Thank you.
Awesome, thank you. Let's thank our speaker the Zoom way. Does anybody want to go first?
Yeah, I would like to ask a question. This is Jeff Linsky. My question is, how do you tell the difference between gas clouds and hazes? And in particular, hazes typically are gray. So if you have a mixture of haze and clouds, then the molecular absorption features will get washed out. So that's my question.
With Brewster, there's not anything built into the code to test the difference between if it's a haze or a cloud. It's only parameterized as a cloud in this. So I think I'd have to add something in to try to test if you could determine the difference between a cloud or haze with the data that we have.
Yeah, I would appreciate it if you could do so.
Yeah.
Go ahead, Zach.
Hi, thank you for this wonderful talk. I guess I had questions about like what you actually just said about the like splitting, doing something in between the volume mixing ratio and the chemical equilibrium. And so, but that seems great and exciting, and I'm delighted to see what comes out of it. So I guess I'm wondering for 1416 and I think some of the others, you showed these regions of like a few, like some narrow wavelength ranges where the cloud opacity is like comparable to or just above the gas opacity. Can you help me connect that to like variability studies? Is like, are those the wavelengths where we would expect to see variability if there is from patchy clouds?
So I am not an expert in variability.
Yeah, neither am
but
I.
I think I'm not sure if it's patchy cloud variability in the J band or if you're seeing more patchy cloud variability at longer mid-infrared wavelengths, because you're probing higher up. But I know there is variability in the J band. I'm not sure if that's from these patchy clouds.
Okay.
But variability is something that we're trying to start testing with retrievals to see if that's something that we can distinguish. And if there's, if variability is large enough, can we distinguish that just by looking at, say, two different near infrared spectra? That's something that I'm collaborating with someone on that we're still really working through because they're having a little bit of difficulty. So.
Okay, gotcha. Yeah. But I could imagine it's hard to put together a like full variability spectrum, but if you can do it with twice as many observations as you need for what you're doing here, maybe that's not so bad.
Yeah, the big elephant in the room for variability is if you're doing stitching together different spectra for these retrievals and they're not simultaneous, it's very hard to then make that conclusion. So there are a couple of people that have been working on retrievals with including longer wavelength data, but that's like the one thing you're sweeping under the rug because they're not simultaneous. So if you can get simultaneous observations, it'll be a lot easier to say, where is this variability coming from and what the retrieval can tell us. Because if you have, multiple time slices of this, then you maybe can see this over time with the retrieval and see what's changing, if it's clouds or if it's an abundance thing or anything else.
Cool. Awesome. Yeah, sounds great. Because what you can do in one snapshot here is so amazing. It'd be nice to see it all together. Thank you. That's great.
Thanks.
Any other questions?
Thanks, Eileen. I think I was going to ask about this issue with the radii, and whether it's so unclear, or how clear is it the reason for the low radii in just retrievals in general, or maybe in particular types, and whether additional information, like a prior on the radius from, say, rotation information, resign eyes, things like that, how much more, how helpful would those things be for doing that kind of work?
So in general, the radius problem for retrievals is still a mystery, because with Brewster, sometimes you're seeing things that are intrinsically small, but then for some other objects, I'm seeing things that are okay. And I don't fully understand where this problem is. Other retrieval codes are also retrieving radii that are too small than you would expect. So I don't know if this is like a problem with opacities or pressure broadening that's affecting the radii we get out. But I think if you have a constraint on the radius from some other method, being able to put that in to constrain your values as your prior would probably be a strong piece of evidence to try to get out. It's going to change what you're going to get out in the end from your abundances and the rest of that. So I think adding that in would be really strong for retrievals.
Cool, thank you.
Okay, this is Jeff Linsky again, and I have another question. Namely, variability could be produced by star spots that are they're preferentially located on one hemisphere of the star. And since molecular abundances are highly temperature dependent, if you have a photosphere in which, say, 10% of the area is cool, that can produce a very different, the sum total of the star spot photosphere and the rest of the non-star spot photosphere can look very different in terms of molecular abundances. Any thoughts on that?
So for brown dwarfs, the retrievals have really been done on cooler objects. We're not really seeing star spots. We're seeing variability from clouds. We haven't tried to move, there's people that are trying to move into the late M dwarf regime. That hasn't been tested yet. So I think you definitely need to start thinking about how to do multiple patches to try to see if there's different abundances from different regions that you're going to get out. But then that starts to, the more patches you add and the more parameters, you're starting to run into computational problems. So if you add longer wavelength data, you can end up getting up to like 45 parameters in your model, and we're running out of the computation limits that we start hitting.
Well, it's also a degeneracy issue, but I think people should look into the possibility of, or at least the effect of star spots on the composite atmosphere and on the SEDs.
Yeah, definitely.
I think I have a silly question. It seemed, I'm not sure if I was reading this correctly, but the cloudiness of your subdwarf was dependent on its age. Is that real? Did you say that in a plot?
I did not say that in a plot. It might have been the plot where I was comparing young objects to the subdwarfs, where the young objects were really cloudy. and you were noticing the difference between young objects being cloudy and the subdwarfs being primarily cloud-free.
Right. Is there, like, why is that? Are these things like, no. I don't know if this is a question. Are these things evolving? Are their atmospheres like changing over like long time scales? Like if you look at a 10 billion year old object versus 3 billion year old object, does that make sense?
Right. Okay. So brown dwarfs do evolve over time, but for the subdwarfs, these objects formed without clouds. Because they have these lower metallicities, they're not able to condense particular features out into clouds in their atmospheres. So these things are already
that
cloudless.
Makes so much sense. Thank you so much. Okay, glad I asked that. Any more questions, or should we thank our speaker again? I'm looking to see if people are unmuting. All right, thank you so much, Eileen. That was great. We never have just star talk, so I was so excited. Great. Yeah. All right. Bye, everybody. Thank you so much.